Tonight I want to try to generalize a very old IMO problem, an International Math Olympiad problem all the way back in 1960. Now I'm going to stipulate this constant is greater than 0 just for inequality processing. Now, you guys, you can see the problem here. Here's the original problem all the way again. It's number 2 back in 1960. We're trying to find a solution interval for this inequality. Now you can see the relationship here. We have a 2 and a 2 squared and then a 2 right there. And that's what I've written down here. So what I'm trying to generalize it, and I want to get a solution in terms of K and C. Okay, now the very first thing before we get into the actual processing is we have to ensure that this radicand is non-negative. So that's the same thing as saying 1 plus kx is greater than or equal to 0. And of course you get that x must be greater than or equal to minus 1 over k. Now notice k greater than 0 actually got applied here. If k was less than 0, this inequality would be reversed. All right. Now, so x is trapped between 0 and minus 1 over k. Notice 0 has to be excluded because notice that if x were equal to 0 right here, you would have something over 0, right? You would have the numerator, I won't write it down, but you would have a division by 0 right here if x were equal to 0, right? Okay, folks, again, if x were equal to 0, that would make this 1 minus 1 down here, and we'd be doing an undefined divide by 0. So that explains why we have to have the strict, while we're excluding 0, as you can see right here. Okay, now that that's out of the way, let's get into the funner part of the problem, the processing of it. So again, here's our general form right here. And it's fairly straightforward. I start the processing on the left-hand side here. I'm just going to work on the left-hand side and then insert this when we get to the right moment. But notice right here, the part that works here is multiplying through by the conjugate of the denominator, quantity squared. Now notice this is in the form a squared. And I'm just writing down the form so I won't have to write as much. But so we have an a squared where a is equal to 1 minus this stuff. And then this part over here is b squared. But notice what we can do right here. This works out very nicely. You can rewrite this just properties of exponents. A squared b squared by the commutative property is the same thing as a times b quantity squared. Okay, ab quantity squared. Now that kind of eluded me when I first started thinking about this problem. Simple laws of exponents. You see, we have an object squared times an object squared. But by laws of exponents, you can bring them together by commutativity. And you get an object squared times an object squared is equal to the product of the two values quantity squared. Now, why is that important? Because you see, when you do that to this, you would actually get minus, and I'll put that there for emphasis so I don't have to write all this out, minus kx quantity squared. Now, I don't want to belabor this point too much, but that's what's so nice about this choice of your algebraic steps. And you can see exactly what happens here. Everything goes away. You're left with a minus kx quantity squared when you do a minus b times a plus b. Okay, folks? And of course, this squared is the k squared x squared that you see right there. Now, nice thing happens there. This is going to cancel out on us. All right, and so we get that this is just equal to this, right? The k squared x squared terms just canceled out nicely. Now, this is just the expansion right here. This is just the expansion of this. And so again, at this point, once we have this, we put kx plus c to the right of it because that's what we've shown, that all of this is equivalent to this right here, okay? And so now we're back to the original inequality equivalent form, believe it or not, okay? And then just nice things happen here. The kx is canceled, right? And so you end up with this statement right here. And the rest of it, I'll try to just be a little quieter about things. 1 plus kx is less than all of this. And again, that's pretty clear why that's true, folks. Now, this is probably almost insulting here, but 1 is the same thing as 4 over 4, right? So when you subtract it, okay, 1 is the same thing as 4 over 4. And so when you subtract 1 from this side, the 4/4 go away, and divide by k, and you get x is less than this expression right here. And so we have everything in terms of the constant on the right-hand side, and then the constant k. Now let's look at that IMO problem and see how that works out. Okay, so here's the original IMO problem. I just repasted it in there, and I'm using our result here that says that x has to be strictly less than c² minus 4c over 4k, and you get 45 over 8. And this is the solution, and this is just what we did at the very beginning of the problem. And so the solution interval for this IMO problem is what you see, minus 1/2, but x between minus 1/2 and 0, or x between 0 and 45 over 8. Okay, again, this says x is less than 45 over 8 after you do the arithmetic here. Okay, now, so that's the IMO problem. Now, last thing here, and we'll be done. I made up my own here. So this is in the form of the IMO problem. You have a constant squared, the constant, and the constant here, and then the other constant, which we'll call c. Now right here, of course, let's see here, k, what do we have here? K is equal to 7 right here, right? Okay, and cap c is, of course, equal to 15. And so there we go, folks. This is the rest of the processing here. This is all just arithmetic stuff. I won't bore you with it. But this would be the solution interval for this made-up problem that very much resembles the 1960 IMO problem. But anyway, folks, I hope you enjoyed that. I thought it's kind of cool. The algebra is kind of nice. It produced a fairly manageable formula that expresses the solution set in terms of the two constants.